Hi class, welcome to lecture 8, Regression with Binary Outcomes. In today's lecture, we'll briefly discuss moderation, and then we'll talk about two ways to run regressions with binary outcome dependent variables. So first we'll talk about linear probability models, as well as logistic regression models. All right, so moderation. Moderation is when a third variable affects the relationship between your main independent and your main dependent variables, excuse me. It's this third variable that's oftentimes some baseline characteristic. It's maybe an indicator of group membership that we want to see whether it has a differential effect for the main independent variable. So again, it can be something such as gender, socioeconomic status, etc. You can conduct moderation analyses in Stata easily with the interaction term that you can either create manually, or you can include the double hashtag operator in your regression line. Now, moderation is not to be confused with mediation. Mediation is, whether this other variable is posited to be the variable through which the main independent variable exerts its effect on the dependent variable. So it's supposed to be this mechanism that is what is driving the effect or the relationship we see between the independent and the dependent variables. So we can formally do this in Stata. I've done so in my own work where I've used a college degree as a mediator between the relationship between the parents' occupation and child's occupation. And I find, if you're interested, that a college degree has only a small mediating effect on the relationship between public sector work. So why might we be interested in binary outcome variables? So thus far, we've mainly dealt with continuous variables such as test scores, right, with our Lubbock and ECISD data sets. Sometimes our dependent variable might be some sort of qualitative event that we want to examine changes in, right, with our covariates. So we can look at something such as graduation, teacher turnover, whether or not a student was suspended as our dependent variable. So in this case, our dependent variable, which we've seen in other domain coding scenarios, takes on a value of 0 or 1. In this case, 1 indicates success, whether the condition is met, and then 0 signifies failure, where the condition is not met. There's no value associated with success or failure in this case. It's just an indicator of whether we turn on the light switch or we turn off the light switch, or whether the condition was met or whether it was not met. So in this case, we have an example of college enrollment, right? Those students who enrolled in college, let's say after high school, would get a 1, and those that did not would get a 0. They did not meet this condition. So typically we're interested in the probability of these events occurring, right? It wouldn't make much sense to say, what is the expected value of college enrollment given these other covariates, right? This is what we've done so far with our OLS and our continuous variables as our dependent variables. Again, here's our conditional expectations model, where we have the expected value of y given x and our list of covariates. So whenever y takes on a value of 0 or 1, then we have the probability, or the response probability, right? Where the probability of y equals 1 given x is equal to our conditional expectations model. So if we want to plug in our response probability into this equation above, we have this linear probability model, which is very similar to our OLS, or it is OLS essentially, but with the binary dependent variable. And again, in multiple regression, which is what we're doing now, our beta coefficients represent changes in the probability of success. Again, success being whether the y condition or the y variable is equal to 1 and 0 otherwise. When we increase our x by 1 unit, holding all our other variables constant. So this is, I like this way of putting it in the bottom. Our delta p, or change in the response probability, is equal to our beta sub j delta x sub j. So our change in the response probability is equal to the beta coefficient associated with the change in x. So 1 unit increase in x is associated with, this effect on y. And so since our dependent variable is limited, that is, it takes on a 0 or 1 value, we can't interpret our coefficient estimates the same way we did when our dependent variable is continuous, right? Before, we would say our beta estimate is the change in y given a unit increase in x. It doesn't apply in this situation because our dependent variable only takes on a value of 0 or 1. So rather, we interpret our changes as how the average of y changes when we increase x a unit, x 1 unit, all else equal. And so we arrive at this, where the linear probability models approximate average partial effects on the probability of success in the case where our y equals 1. So we're looking at averages for the group, for our sample. We interpret these beta coefficients as percentage point changes. So for example, when you run your regression with your binary outcome, the coefficients on your dummy variables or your continuous variables, whichever the case, represent percentage point changes. So for example, an estimate of 0.06 is a 6 percentage point increase in the probability that y occurs given x. Excuse me. Let's say we're interacting a variable and our coefficient increases to 0.10. Then this represents a 4 percentage point increase in the probability of y occurring given x. And as we've seen before, we can calculate percent changes using our percent change formula. So this increase of 4 percentage points represents an increase of 66% from the base of 6 percentage points. So some of the pros or the benefits of the linear probability model is that the coefficients are easily interpretable as average partial effects, marginal effects. We can incorporate interaction terms easily and interpret those as such. Even though there may be some difficulty in interpreting them, we can still make sense of them. And the linear probability model also works well when the values for our independent variables are around the average for the sample, right? So we can't have like an uneven distribution of values for our independent variables, or else it might lead to some of the issues associated with LPMs, which we'll see in the shortcomings. So for example, if we plug in certain values for our x variables, it can produce estimates or predicted probabilities rather that are outside of our 0, 1 range, which doesn't make sense because since we're dealing with probabilities, they have to sum to 1, or they have to be within the range of 0 and 1. So it doesn't make much sense to have predicted probabilities that are less than 0, which would be negative, or greater than 1. Relatedly, since it is a linear model, linear probability models assume constant effects across various levels of an independent variable. So for example, let's say we're interested in the relationship between school suspensions and expulsion from the school. So let's say we have our y and our x variable in our regression model, and we see that the coefficient estimate on our independent variable, which is the number of I think it was suspensions, which could be a count variable. Let's say the coefficient on that is 0.30, right? 30 percentage point. It's associated with the 30 percentage point increase in the probability that a student will be expelled. So linear probability models assume that this effect is constant across all levels of a variable. So let's say a student has, let's say, 4 suspensions in a school year. If we multiply our 0.3 estimate by 4 for let's say a student that has 4 suspensions, it'll produce a predicted probability of 1.2, which doesn't make sense because again, our dependent variable takes on a value of 0 or 1, whether the student was expelled or not. And so this is one of the drawbacks about a linear probability models. It assumes that the effect is constant across levels of a independent variable. I think I kind of tied into the first two since they're related. Additionally, the linear probability models are inherently they contain heteroscedasticity. This is because the error terms for our linear probability models are not normally distributed. It has a binomial distribution. But thankfully we can correct for this, usually by including our robust little r option at the end of our regression line as theta, or better yet, we can cluster our standard errors according to some clustering variable. So for example, we can cluster, we usually cluster at the highest levels. We can cluster at the school level, let's say, if we're looking at teachers within a school. And then the third point there is that the Euler's mechanics from before applying LPMs, we rely on the T and the F statistics. So it's necessary to address or to fix the standard errors in the linear probability models, because they're on their own. If you don't correct for it, they're invalid. But we have this easy fix that we can incorporate into our regression line. So again, we use the T and the F statistics as before. And so we have this goodness of fit measure for linear probability models. It's called the percent correctly predicted. So it has, we have our observed values for Y, again, that take on 0 or 1s, and then we can calculate our predicted probabilities and see how that compares to our observed data. Did the model, or what percentage did the model correctly predict in the observed data? And so typically there's this threshold of 0.5 or greater that is assigned to 1 for success. And then anything below this is considered a 0. And so this kind of helps keep the bounds between 0 and 1, our predicted probabilities between 0 and 1 as well. So now moving on to logistic regression. It's a linear alternative to modeling binary outcomes. As we'll see with our OLS regressions and our linear probability models, it follows this linear model that we've seen before, right? This straight line modeling our X and our Y variables. However, with the logistic regression, it'll take on an S shape, which I'll have a picture in later. But essentially, the logistic regression uses this G function to restrict the range of estimated predicted probabilities to be between 0 and 1. Right, so there's a lot of stuff that's going on behind Stata that we don't have to worry about, thankfully. But so you can see it, it's this function that restricts our values so that we always get predicted probabilities between 0 and 1. And so below we have this logistic function, which is a fraction of the expression of Z over the 1 plus expression of Z, where Z is all real numbers. In practice, in Stata, you would just include logistic or logit, your Y variable, and then followed by your independent variables. All right, so here's a picture comparing our linear regressions and our logistic regression. We can see that on both, since they both have this 0-1 binary outcome, or since they are this binary outcome measure, there's pileup at the 0 and 1s. There's nothing in between. As we've seen before, the linear regression approximates the linear relationship between our X and our Y. And again, we acknowledging that our predicted probabilities can fall out of this range between 0 and Y. However, on the right, we see the logistic regression, which takes on this S-shaped form, which is the better fitting model for, or better fitting model for binary outcomes, and we can see that it touches on most of the zeros and ones, and then this jump signifies the change going from 0 and 1. And the asymptotic line, you can see, will always keep our predicted probabilities between 0 and 1. And so with OLS, we use least squares estimation to estimate our coefficients. In logistic regression, we use maximum likelihood estimation. So it's choosing the best S-shaped curve that maximizes the log likelihood of our data. So whichever function fits our data best. And what Stata does is it rotates this S line on each data point and finds the one that best fits the data. And so we'll see in this data output that our logistic regression models have log likelihood numbers associated with them. They're always going to be negative because we're taking the log of a value between 0 and 1, and smaller negative numbers. So smaller negative numbers, which are large, like the absolute value is large, or larger, I should say, represent poorly fit logistic models. Whereas log likelihoods that are closer to 0, so the absolute value of these are smaller, but they're greater since they're closer to 0, are supposed to be better fitting models. And similarly, we have our pseudo R-squared, which is not the same R-squared that we get in from linear regression, but it's something that we can use to compare. And there's multiple pseudo R-squareds that we can use. However, there's a default one provided from Stata. We can also conduct a likelihood ratio test to tell us whether two models are significantly different. If they are, then the model with more predictors is said to be the better fitting model. All right, so we can also calculate this by hand. Again, if we're looking at the log likelihood, which is this negative number, in this data output, we can subtract the unrestricted model, or the model with more predictors. We can subtract the restricted model from that. So the model with fewer predictors, and then we can multiply it by 2, and that gives us our likelihood ratio test statistic, which we can then look up, if we're going the old school way, in a table. But thankfully, Stata has this, or Stata produces this when we run the likelihood ratio test. I've included that code here in the notes in the PowerPoint, so you can follow along if you want to perform it yourself. Like in OLS, we can also obtain our walled statistics, so we can simultaneously test whether different coefficients or different parameters that we've estimated are jointly significant, right? So whenever we run our regular regression, we're testing an individual null hypothesis for one variable. The wall test, on the other hand, allows us to simultaneously test multiple null hypotheses. The null hypothesis is that these coefficients are equal to some value. In this case, it's often 0. And then whenever we reject that null hypothesis, then we determine that, we conclude that they are different from 0 or whatever value that you have assigned. But we can also do this with logistic regression. So some of the benefits or the pros of logistic regression are that our predicted probabilities are always going to fall between 0 and 1. Another benefit of the logistic regression is that it accounts for different levels of an independent variable. So going back to our suspension scenario, the effect of suspension on expulsion, we had this initial effect, or this effect of 0.30 for a 1 unit increase, right? In logistic regression, it assumes that there's marginal diminishing effects for each additional suspension. So while the first let's say, well, 1 unit increase in the amount of a 1 unit increase in suspension is associated with the 30 percentage point increase in expulsion. Let's say we're going from 1 suspension to 2 suspensions, then this effect will likely be smaller, right? I think if we're thinking in terms of economic theory, right, a second suspension is going to have a smaller effect on expulsion, and then taking it further, a third suspension, going up from 2 to 3, it's going to have an even smaller effect, right? So it accounts for that, for these diminishing marginal effects. However, one drawback of logistic regression is that the regression parameters that are produced are in terms of log odds, right? So we have to do something with that because they're not easily interpretable. So we need to apply some transformation, which we can do easily in Stata, and we'll go over to on the following slides. So first, and the more common one, transformation that we make is to transform these log odds to average partial effects or average marginal effects. They go by different names. But these are essentially the average of the individual partial effects for the sample. So what Stata does, which thankfully we don't have to do it, is it calculates the effect for each of the independent variables. Let's say our independent variables in X is a 0, 1 variable. It calculates the effect, or it calculates the difference between going from 0 to 1. So it calculates 2, it takes the difference and it averages these across all individuals in the sample, hence the name average partial effects. Now these are preferred to odds ratios below because they are more similar to our estimates from our linear probability models. Again, we interpret these as percentage point changes in Y associated with an increase, a 1 unit increase in X. These are more easily interpretable and more different. For example, economists use the percentage points often. So it makes these understood by a larger audience. We also have odds ratios, which is the ratio of odds of an event occurring for one group to the odds of an event occurring for another group. I think we have some examples here, but I'll just say odds ratios I haven't seen them used very much. Maybe it's some kind of cult following, but yeah, most people I would say use average partial effects when using logistic regression. All right, so we have some Stata output from the SAS and the TFS. So SAS is the School and Staffing Survey, and the TFS is the Teacher Follow-Up Survey. This is publicly available on the NCES website. And these are for the school years, the 2000 and the 2001 school years. All right, so it's, they surveyed a bunch of teachers in the 1999-2000 school year, and then they surveyed them a year later in the 2000 to 2001 school year, and they tracked whether or not they were still teaching in the same school or whether they were teaching more generally. So we have a logistic regression where the outcome is a binary indicator variable equal to 1 if the teacher taught at a different school, or the teacher was not teaching at the same school in the TFS as they were in the SAS. Again, let me repeat that. So the outcome variable is a binary variable indicator equal to 1 if the individual was not teaching in the TFS, they were not teaching at the school as they were in the SAS. So again, in the SAS, the initial round of the survey, we have teachers who everybody's teaching, right? Because they're teachers. And then we have an associated school ID with them. And then in the TFS, there's this outcome indicator. There's this outcome variable indicating whether the individual was still teaching, whether they were teaching at a different school, or whether they left teaching altogether. I should have explained that before, but hopefully that kind of better explains or contextualizes this turnover variable. So we're looking at whether teachers were teaching somewhere else or not at all. in the teacher follow-up survey. Then I have some dummy variables included here, gender, dummy variables for age. In this case, younger is equal to less than 30. Older is equal to 50 or more. I didn't come up with these. These were determined by the SAS, so don't tell me anything. And then we have middle age, which is our reference category. And then we have this one where female is our reference category for gender. We have our race variables. The reference category here is non-Black, non-Hispanic, mostly white teachers. And then we have school level indicators, so primary and secondary. Here, our reference group is schools that have both primary and secondary together. We've also applied probability weights to our regression. And then we've clustered our standard errors according to the school, since multiple teachers were surveyed from the same school. So we have our logistic regression, and we see the output below. Again, so keep in mind that these are presented in terms of log odds. We see our wall statistic, our probability is significant, which suggests that this model is better fitting than a model with no predictors. We have our log pseudo likelihood, but we won't pay attention to that too much. We have our pseudo R squared, which is 0.01, which says that that 1% of the variation in the dependent variable, or our Y variable, is explained by our variables in our regression model. So looking below at the table or the coefficients, I want you to pay attention mainly to the signs of the coefficients, and then also the p-values. So we can see some negative signs. We also see just one statistically significant p-value. Just keep those in mind. The signs are indicative of the direction of our effect. However, our p-value tells us whether or not this variable is statistically significant or different from 0. So we'll use the margins command in Stata to transform our log odds to average partial effects. We'll use the option dydx to make this transformation. And then we have our coefficients transformed into average partial effects or percentage points. So remember, looking back to our younger one, our younger variable was the only one that was statistically significant, and this sign was positive. So we might hypothesize that being younger is going to make you more likely to turn over. The log odds are positive. So now that we have percentage points, we take a look at younger. The coefficient is 0.09, which suggests that younger teachers are 9 percentage points more likely to turn over compared to middle-aged teachers. Let's see what else. So if we want to compare our logistic regression results to our linear probability results, we can do that. I've screenshotted the two outputs here. On the right-hand side, with the OLS, the linear probability model, I have clustered the standard errors at the school level, school ID level, which you can see right there, 4,100 clusters. It's essentially the same regression as before. The output is for logistic regression is from the previous slide. But if we want to take a look at the coefficients, they're pretty similar. They're similar in terms of magnitude, direction, significance. Taking a look at our younger coefficient on the left-hand side, we see it's 0.09 for logistic regression, and for OLS, it's 0.10, 0.11 if you want to round up. These are pretty similar, likely a negligible difference. However, it's up to you which results you want to present in your papers. I think there are mainly disciplinary differences between which results are presented rather. I know economists like to use linear probability models, which would favor the results on the right. And then a lot of other, I think most other disciplines actually prefer logistic regressions. Again, transformed into either odds ratios if you're maybe doing public, like health research, or marginal effects, average partial effects, if you're doing education research, psychology research, and so forth. A lot of the times you'll want to include, if you're using linear probability models, you'll want to include a logistic regression presentation of your results in terms of marginal effects, average partial effects, to show that the results are pretty much the same. Now we can also compute odds ratios from our logistic regression command. So before we used logit in Stata, this time we're going to use logistic, which automatically transforms the log odds to odds ratios. I'll go ahead and interpret the first two odds ratios in our table below, noting that the p-value for male is not significant, not statistically significant. And in the case of using odds ratios, 1 is our reference point. So anything below that is interpreted as a decrease in the odds, and anything above that is interpreted as an increase in the odds. For anything below 1, we're going to take the number 1 and subtract our odds ratio from that. So in the case of male, 1 minus 0.87 leaves us a difference of 13.13. So we can say that the odds of turnover for males is 13% lower than the odds of turnover for females, right? Now for our younger dummy variable, we see that the odds ratio is 1.99. So we can say that the odds of turnover for younger teachers are 1.99 times greater than they are for middle-aged teachers. If you want to practice interpreting the remaining coefficients or the remaining odds ratio, you can do so. Now, some last notes on logistic regression. There's other types of logistic regressions. There's multinomial and ordered. In our previous example of turnover, we modeled a binary dependent variable that takes on a value of 0 or 1 for whether or not the teacher turned over. We can also use multinomial logistic regression to look at nuance within our dependent variable. So we combined, in our turnover variable, we combined teachers who went to a different school and teachers who left teaching altogether into one group. This multinomial logistic regression allows us to keep this nuance in turnover. So we can look at teachers who stayed teaching at their same school. We can look at teachers who moved to a different school, who would be considered movers. And then we can look at teachers who left teaching altogether, leavers. There's other kinds of categorical variables that you can use, but we can use this teacher one as an example here. We also have ordered logistic regression, and this is when our dependent variable takes on this ordered ranking. Oftentimes, this is a Likert scale. For example, we can use satisfaction with teaching as our dependent variable, where 1 equals not at all satisfied and 5 equals most satisfied. So this has been a brief introduction on regression with binary dependent variables. I'll go ahead and include the notes in this PowerPoint on Blackboard. Thank you.